Horizontal asymptotes of a function represent a value that the function is approaching. An example of this situation would be Newton's law of cooling. If I was to bring in a hot cup of coffee and set it down in a room, initially I would expect the temperature of the coffee to be very high. So we began with a very large temperature. And as time goes by, the temperature begins to cool. Very, very important with Newton's law of cooling. It's not going to cool forever. The temperature will not go negative all the way down to absolute freezing. But what will happen is the temperature will approach however warm or cold it is in the room. This is called the ambient temperature. For all practical purposes, let's say the temperature in the room is 72 degrees Fahrenheit. Now, what will happen is the coffee will begin to cool a lot at first, but as it gets closer and closer to the temperature of the room, it begins to cool slower and slower. The reason is the coffee is only changing temperature because the difference between its temperature and the room. Sort of like a rubber band. As it gets closer and closer, there's less pull down on the temperature. And what happens is, over time, my temperature is approaching 72 of my cup of coffee. This is an example of a horizontal asymptote. According to Newton's law of cooling, it never actually reaches 72, but that's not really relevant for our part. What we're concerned is that the temperature is approaching 72. And I would write this, basically let's let little t equal our time, and I'll let F be our temperature in degrees Fahrenheit. So, I can say, as we move forward in time, and basically we're not at infinity, we're just saying it can go forever and ever and ever as long as we want to let it go. The temperature in Fahrenheit is approaching, it's not going down forever, it's not going to negative infinity, it's approaching the room temperature, for our purposes, or ambient temperature, of 72 degrees. So, as my temperature increases, as my time increases, my temperature in Fahrenheit is approaching 72 degrees. Now, this is one type of notation we can use. We can also use another type of notation called a limit notation. With limit notation, I would say that the limit as t approaches infinity of f is 72. Now I'm color-coded so you can see as we go from one way of writing it to another way of writing it. One with limit notation, one without limit notation. The idea is exactly the same. They read a little bit differently. The limit of f is 72 as t, that's an arrow, approaches infinity. Another example is our famous rabbit example. We take an island, a small island, and we put a couple of rabbits on it. And the rabbits begin to multiply relatively quick at first. And we end up with more rabbits, and they're multiplying and multiplying and multiplying. But eventually, we begin to run out of space, which means we begin to run out of food for the rabbits on the island. And the population begins to slow down. And as it slows down, it reaches closer and closer to an amount which we call the carrying capacity of the island. This we consider a amount that the island can sustain. In this case, we'll say that our carrying capacity is 1,000. So, no matter how many years you will have the rabbits on the island, they're going to get closer and closer to 1,000 rabbits on the island in an ideal, perfect situation. Clearly, that doesn't exist in the real world, but we can imagine that. There's only so much room for the island, and these rabbits are approaching that barrier. So, we would say, for our sake of purposes, two different ways we can write this. As y, the number of years increases, the number of rabbits is approaching, with an arrow, 1,000. With limit notation, we would say the limit as y approaches infinity of n, the number of rabbits, is 1,000. Which limit is quite applicable here. That's the limit of how many rabbits can be on the island. So we're approaching that limit. And again, we can approach the limit from the top or from the bottom. Another example might be your shocks on your car. I'm going to let L be the length that your shock is at any given time, T, in seconds. So let's say you're driving down the car and your shock absorber is this long, and you hit a bump. As you hit that bump, your shock absorber becomes compressed and the length begins to decrease. After the bump, so it begins to decrease, and once you pass the bump, it begins to increase. And it doesn't just come back to the original length, but it actually goes past it for a little bit. That's why you get the little jump in the road. And then, over time, hopefully quite quickly, if your shock absorber is working well, it begins to level out. And as over time, your car's ride goes back closer and closer to its natural state of how long your shock was in the first place. And so basically what happens is this would be called a dampening oscillation. So we're oscillating back and forth, but clearly the oscillation is getting smaller. And the length of your shock then, let's call the original shock as 21 inches long. So it got compressed, I don't know, maybe to 10 inches, then it sprung back up to 30 some inches. But after a while, the shock does its job and brings its car back to the resting place. So, we can say that as time moves forward, the length of the shock is approaching 21. Notice, it goes from shorter to longer to shorter to longer to shorter to longer to shorter, back and forth oscillating. We can cross that. It's not a problem. The limit, the horizontal asymptote, is not a boundary that cannot be crossed, but it is something you are approaching. So another way of saying that is a limit as time goes to infinity of the length of the spring, our shock, is 21 centimeters.